Mercury is the planet closest to the Sun, lying just about 36 million miles away. Despite its unique position in our solar system, Mercury was long thought of as a barren, unremarkable world. But recent discoveries show that Mercury has some remarkable features that make it much more interesting than it first appeared. Surprisingly, Mercury has water ice at its poles, a finding that startled scientists given the planet's intense heat near the Sun. Additionally, Mercury's surface is dotted with rare impact craters and unusual landforms that aren't found on other planets. These features add to Mercury's mystery and suggest that it's experienced a fascinating geological history. Though Mercury is small, it has a magnetosphere that's a magnetic field that can deflect some of the Sun's charged particles. It even has a very thin atmosphere, or exosphere, which is surprising for a planet so close to the Sun. This magnetosphere and thin atmosphere, while weak, provide clues to the planet's inner structure and past conditions. Mercury is a small, rocky planet with a radius of about 1,516 miles, making it just slightly larger than the Earth's moon. It's the closest planet to the Sun, orbiting at an average distance of 36 million miles. A year on Mercury, or the time it takes to complete one orbit around the Sun, lasts only 88 Earth days because of how close Mercury is to the Sun. With almost no atmosphere to trap heat, Mercury's temperatures vary drastically. During the day, surface temperatures soar to around 800 degrees Fahrenheit, while at night, without the Sun's warmth, they plummet to a chilly -290 degrees Fahrenheit. One day on Mercury, meaning the time it takes for the planet to rotate once on its axis, is extremely long. While Earth completes one rotation in 24 hours, Mercury takes about 59 Earth days to finish a single rotation. Mercury's rotation is influenced by something known as a spin-orbit resonance. For every 3 times Mercury rotates on its axis, it completes 2 orbits around the Sun, which creates a unique 3-to-2 relationship. This resonance means that during its orbit, Mercury turns slowly enough that its day is almost 2/3 the length of its year. Scientists used to think that the Sun's gravitational pull had tidally locked Mercury, meaning one side would always face the Sun. However, Mercury's actual spin-orbit pattern suggests a different story. One theory is that Mercury might have been in a different spin state long ago. Some scientists believe a massive collision could have shifted its rotation to the current 3-to-2 pattern. Another study, led by Benoit Noel and his team, suggested that Mercury could have been in its current resonance state since its formation. This ongoing research helps explain why Mercury's rotation and orbit are unlike those of other planets. Mercury's orbit is quite different from that of other planets. Instead of being a perfect circle, its orbit is more elongated or eccentric, stretching from about 29 million miles to 43 million miles away from the Sun. This means that at certain times, Mercury is much closer to the Sun than at others. This uneven orbit not only causes big temperature swings, but also makes Mercury's speed change as it moves around the Sun. When it's closest, or at perihelion, Mercury zips along faster. Then, at its farthest point, or aphelion, it slows down. This unusual orbit impacts everything from Mercury's surface temperatures to how its weak magnetic field interacts with solar winds. One of the most surprising discoveries around Mercury is a dust ring that lies along its orbital path. Dust rings are created when particles from meteoroids get trapped in a planet's orbit. Although Mercury's dust ring is faint, it's still significant because it adds to our understanding of the solar system's debris environment. Meteoroid impacts on Mercury's surface may throw dust into space, which gets pulled into orbit by the Sun's gravity. This dust ring could also help us learn about other inner planets and the origins of cosmic dust in our solar system. Mercury's magnetosphere is weak but unique for a planet so small and close to the Sun. This magnetic field, while not as powerful as Earth's, still manages to push back some of the sun's charged particles, creating a protective layer around the planet. However, this magnetic shield isn't strong enough to keep all solar wind out. Observation by NASA's Messenger spacecraft revealed magnetic tornadoes, twisting funnels of magnetic energy that allow solar wind particles to leak through Mercury's magnetosphere. These magnetic tornadoes, and the leaky nature of Mercury's magnetosphere, contribute to unusual space weather conditions on the planet's surface, shaping its environment in ways we're still trying to fully understand. Mercury has an exceptionally large core for a planet its size, with metallic elements like iron taking up about 1/3 of the planet's total mass. This makes Mercury one of the most metal-rich planets in the solar system. Its core is not only massive, but may also still be partially liquid, as scientists discovered from the way Mercury's magnetic field changes. This liquid core might be responsible for generating Mercury's weak magnetosphere, similar to how Earth's core generates its magnetic field. The formation of Mercury, with its high metal content and dense core, raises intriguing questions. One theory is that Mercury formed close to the Sun in a metal-rich part of the protoplanetary disk, the cloud of gas and dust that gave birth to the planets. In this environment, heavier metals may have clumped together to create a dense, metal-heavy planet like Mercury. Another theory suggests that Mercury may have started out much larger, but lost much of its rocky outer layers. Some scientists propose that huge impacts from other large space objects or the gravitational influence of Earth and Venus could have stripped away Mercury's outer material, leaving behind its metal-rich core. If true, this would mean that the Mercury we see today is a survivor of intense planet-shaping events in the early solar system. Studying Mercury isn't easy, mainly because of how close it is to the Sun. From Earth, we can only see Mercury for short periods during sunrise or sunset, when the Sun's glare isn't overwhelming. Even then, Mercury's small size and distance from Earth make it hard to observe in detail. This limited viewing window means astronomers need to use specialized telescopes and careful timing to gather information. Sending spacecraft to Mercury is a complicated task due to the Sun's powerful gravitational pull. Spacecraft traveling toward Mercury accelerate quickly, and slowing down enough to be captured by Mercury's gravity requires a lot of fuel and careful planning. Additionally, the intense heat from the Sun make it challenging to design spacecraft that can survive the extreme temperatures near Mercury. The first mission to explore Mercury was NASA's Mariner 10, which launched in 1973. Mariner 10 was a pioneer for several reasons, using Venus's gravity to slingshot toward Mercury, a technique called gravity assist. This maneuver allowed Mariner 10 to make 3 flybys of Mercury between 1974 and 1975, capturing detailed images of Mercury's surface for the first time. Through these flybys, Mariner 10 uncovered Mercury's magnetic field, a surprising discovery given the planet's small size and lack of a thick atmosphere. It also found clues about Mercury's metallic core, which makes up a large part of the planet. Mariner 10's images revealed a surface covered with impact craters and smooth plains, giving us our first real look at Mercury's rugged landscape. NASA's Messenger, Mercury Surface Space Environment, Geochemistry, and Ranging mission was the first spacecraft to orbit Mercury, launching in 2004 and remaining active until 2015. Messenger orbited Mercury over 4,000 times, gathering extensive data on the planet's composition, geology, and magnetic field. One of its primary goals was to create a full map of Mercury's surface, which it successfully completed. Messenger also found evidence of volcanic activity and studied Mercury's weak magnetic field in detail, revealing that it's slightly offset from the planet's center. Messenger's instruments detected water ice at Mercury's poles, where deep craters shield the ice from the sun's heat, offering a surprising clue that even a planet so close to the sun could host frozen water. Messenger made several groundbreaking discoveries. It revealed that Mercury's surface has a unique chemical composition, different from that of other rocky planets, hinting at its distinct formation history. It also found signs of ancient volcanic activity, which helped shape parts of the planet's surface. Additionally, Messenger's observations confirmed that Mercury has water ice deposit at its poles and revealed a mysterious shift in its magnetic field, slightly off-center from the planet's core. Mercury's surface is a mixture of rugged craters, relatively smooth plains, long ridges, and shallow troughs. The craters vary in size and are scattered across the planet, with smoother plains filling some areas. These plains are likely the result of ancient volcanic activity that smoothed over parts of the surface. Additionally, Mercury's terrain reflects its long history of meteor impacts, volcanic events, and the effects of cooling and shrinking over time. Impact craters are one of Mercury's most prominent features, and they come in two main types: simple craters and complex craters. Simple craters are small, bowl-shaped depressions, while complex craters are large with central peaks or ring-like structures formed by the rebound effect of an impact. The largest crater on Mercury is the Caloris Basin, stretching over 960 miles across. Other notable craters include Rembrandt, which shows signs of planetary tectonics, and several smaller craters with unique features. Mercury's craters preserve a record of impacts going back billions of years, offering clues about the planet's formation and history. Mercury has a few rare types of craters that stand out. Elliptical craters are formed when objects strike the surface at a shallow angle, creating an elongated shape. Polygonal craters have edges that form straight lines or corners, thought to result from Mercury's crustal stress patterns. Ghost craters are old craters that have been filled in by lava flows, leaving faint outlines, while ray craters have bright streaks radiating from them, formed by ejected material from recent impacts. These unique crater types reveal the variety of processes that have shaped Mercury's surface. Unlike Earth, Mercury has very few high mountains, or large mountain ranges. The planet's surface has some ridges and escarpments, steep slopes found as Mercury's interior cooled and contracted over time. This contraction caused the crust to wrinkle and form these ridges, some of which stretch for hundreds of miles. These features are clues to Mercury's shrinking size, a process that has shaped much of its surface. One of Mercury's most unusual surface features is its hollows. These are shallow, irregular depressions scattered across the surface, with bright edges that make them stand out. Scientists believe these hollows may have formed as Mercury lost volatile elements, substances that vaporize easily. When these elements escaped into space, they left behind hollowed-out areas in the crust, a process that likely continues even today. Mercury's smooth plains are relatively flat regions, likely formed by volcanic activity. Unlike the rugged, cratered terrain that covers much of Mercury, these plains have fewer impact craters, suggesting they're younger than other parts of the surface. Volcanic eruptions may have poured lava across large areas, filling in old craters and creating smoother land. These plains add to the evidence that volcanic activity played a significant role in shaping Mercury's surface, especially in its early history. The European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, joined forces to launch Bepi-Colombo, a mission to explore Mercury more deeply than ever before. Launched in 2018, Bepi-Colombo is named after Giuseppe Bepi-Colombo, an Italian scientist who studied Mercury's orbital path and helped with Mariner 10's successful mission. This mission represents an exciting opportunity to uncover many of Mercury's secrets that remain unknown even after previous missions. Bepi-Colombo's main objectives focus on studying Mercury's magnetic field, mysterious surface features, and even the water ice discovered at the planet's poles. Unlike previous missions, Bepi-Colombo is equipped with two orbiters that will work together to provide detailed data from different perspectives. One orbiter, the Mercury Planetary Orbiter, will map the surface, analyze surface composition, and search for evidence of volcanic and tectonic activity. The other, the Mercury Magnetosphere Orbiter, will focus on studying the magnetic field, magnetic tornadoes, and how the solar wind interacts with Mercury's magnetosphere. Together, they'll study Mercury's strange hollows, bright, shallow depressions that appear unique to the planet, and investigate how they were formed. Scientists are also interested in how Mercury's surface changes over time, especially due to its intense temperature fluctuations. Bepi Colombo will observe these temperature shifts and look for surface changes, which could give clues about Mercury's composition and how it has evolved over billions of years. The mission will also study water ice deposits at Mercury's poles, protected from sunlight in shadowed craters, which is especially surprising for a planet so close to the Sun. After its launch in 2018, Bepi Colombo began a long journey toward Mercury, using gravity assists from Earth and Mercury itself to help slow down and steer it closer to its destination. This complex path will finally bring Bepi Colombo into Mercury's orbit by 2025. Once there, it will begin its observations and data collection, expected to last several years, giving scientists an in-depth look at Mercury that could reveal new findings about the planet and its place in the solar system. The Bepi Colombo mission is essential to helping scientists understand not just Mercury, but also the early history of the solar system. Mercury's extreme environment, its unique magnetic field, and its high metal content make it unlike any other planet. Bepi Colombo's findings could provide insight into how Mercury formed and how it survived close to the Sun's harsh radiation, helping us understand the evolution of other rocky planets, including Earth. The mission will also help scientists learn more about planetary magnetism. Mercury's magnetic field and magnetosphere, though weak and lopsided, are incredibly interesting. Bepi Colombo could explain why Mercury's field is so different from the Earth's and how it behaves under intense solar wind. With its high-tech equipment, the Bepi Colombo mission is expected to answer many questions about Mercury's surface, magnetic field, and history, and perhaps raise new ones. Neptune is the farthest planet in our solar system. It's over 30 times farther from the Sun than Earth. Because of its extreme distance, Neptune is impossible to see with the naked eye, even from the highest points on Earth. The only way to observe it is through powerful telescopes. Despite its large size and striking blue color, it remains one of the least explored planets, shrouded in mystery and awaiting further scientific discovery. Neptune is enormous, about 4 times wider than Earth. Its radius measures approximately 15,300 miles, and it's large enough to fit 58 Earths inside. Unlike terrestrial planets like Earth, Neptune is made of mostly water, methane, and ammonia. These substances exist in icy forms due to the planet's cold temperatures, earning it the classification of an ice giant. Neptune doesn't have a solid surface like Earth. Instead, its thick atmosphere transitions into a dense, slushy mantle made of methane and ammonia ice. Deep beneath this layer is thought to be a rocky core. Some scientists believe Neptune could harbor a hidden ocean of superheated water deep within its layers. Despite the planet's cold exterior, this ocean could exist because of the intense pressure and heat inside the planet. This possibility makes Neptune an intriguing subject for further exploration. Neptune is one of the coldest planets in our solar system. Its average temperature is a bone-chilling negative 360 degrees Fahrenheit. The planet is so far from the Sun that sunlight takes about 4 hours to reach it. Surprisingly, despite these icy conditions, certain areas of Neptune's atmosphere have experienced slight warming, especially near its south pole. This warming, observed between 2018 and 2020, may be linked to seasonal changes that affect its atmospheric chemistry. Despite being cold on the surface, Neptune generates an unusual amount of internal heat. Scientists believe this heat could come from a combination of gravitational compression and interactions with its largest moon, Triton. Another theory is that Neptune may have collided with a large cosmic object in the distant past, releasing enormous energy still detectable today. Neptune emits nearly 3 times more energy than it receives from the Sun. This energy output is one of the planet's biggest mysteries. The tilt of its axis, which is similar to Earth's at 28 degrees, creates long seasons that last for about 40 Earth years each. These prolonged seasons could also influence how Neptune processes and radiates its internal heat. The atmosphere of Neptune is made up of 80% hydrogen, 19% helium, and about 1% methane. along with trace amounts of other gases. While the methane content is small, it plays a major role in shaping the planet's appearance and behavior. You might have thought lately, why is Neptune blue? Neptune's vivid blue color comes from methane in its atmosphere. Methane absorbs red light from sunlight and reflects blue light back into space, giving the planet its striking hue. Interestingly, Uranus, Neptune's neighboring ice giant, has a similar composition but appears pale blue instead. This difference may be due to variations in the density of methane fog in their atmospheres. Neptune's atmosphere is layered with aerosols that play distinct roles. The lower layer contains hydrogen sulfide ice, which is responsible for darker regions near the poles. A thin haze of methane ice particles forms in the middle layer. These particles contribute to Neptune's rich blue color. The efficiency of methane precipitation as snow in Neptune's active atmosphere helps keep this layer thinner than Uranus, intensifying its color. The upper layer is an extension of the middle layer, containing larger methane ice particles. These particles often precipitate as methane snow, creating dynamic weather patterns. Neptune is home to some of the wildest and most intense storms in our solar system. The winds on this distant planet are incredibly fast, reaching speeds of up to 12,200 miles per hour. This makes Neptune's winds the strongest recorded anywhere in the solar system, far surpassing those of any other planet. These high-speed winds fuel massive storms, including enormous cyclones like the famous Big Dark Spot. Discovered in 1989 by the Voyager 2 spacecraft, this storm was about the size of Earth, swirling at incredible speeds. Unlike Jupiter's Great Red Spot, which has lasted for centuries, Neptune's storms are short-lived. They tend to exist for only a few years, typically between 2 and 6, before fading away or breaking apart. Observations by the Hubble Space Telescope have revealed the dynamic nature of these storms. For instance, a new storm similar to the Big Dark Spot was detected in 2018, only to start shifting southward the following year. Scientists expected it to disappear completely, but instead, the storm reversed course and moved back north. To add to the mystery, smaller vortices have sometimes been observed splitting off from larger storms. These smaller patches of turbulence may represent part of the natural life cycle of Neptune's storms. Accompanying these cyclones are bright white clouds known as scooters, named for their rapid movement across the planet. These clouds are made of frozen methane and are often seen hovering near large storms. However, the exact mechanisms that create and sustain Neptune's storms remain an unsolved puzzle. Neptune is surrounded by a delicate system of faint rings, making it one of the few planets in the solar system to have such features. While less prominent than Saturn's famous rings, Neptune's rings are still an important part of its overall structure. They were first observed by Voyager 2 during its historic flyby in 1989. Decades later, in 2022, the James Webb Space Telescope captured new, detailed images of these rings, showcasing their structure and composition more clearly than ever before. Neptune's rings are made up of dust and ice particles, which reflect very little sunlight, making them difficult to observe without advanced instruments. There are 5 main rings, each named after astronomers who contributed to our understanding of Neptune: Adams, Le Verrier, La Salle, Arago, and Gali. These rings vary in brightness, size, and composition. For example, the Adams ring is particularly narrow, while the La Salle ring is much wider but less dense. The rings closer to the planet, such as the Gali ring, contain a higher percentage of dust, while the outer rings are composed of more ice. One of the most fascinating features of Neptune's rings is the presence of bright arcs within the Adams ring. These arcs, given names like freedom, brotherhood, and equality, are clumps of material that stand out against the otherwise faint ring. Unlike the rest of the ring material, the arcs seem to behave in unusual ways. For instance, they change in size over time and even exchange material with one another. This movement and variability are highly unusual and not fully understood by scientists. Some theories suggest that the arcs formed from the remnants of a larger object that broke apart near Neptune. The planet's strong gravitational forces may have trapped the debris into stable formations within the ring. Other researchers propose that Neptune's moons, particularly Galati, played a role in maintaining and shaping the arcs through gravitational interactions. Neptune's moons are a fascinating part of its system, with Triton standing out as the largest and most intriguing satellite. Triton is an extraordinary moon, unlike any other in the solar system. It orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of the planet's rotation. This unusual orbit suggests that Triton did not form alongside Neptune, but was likely captured later. Scientists believe it originated in the Kuiper Belt, a region of icy objects at the edge of the solar system, before being pulled into Neptune's gravitational embrace. What makes Triton even more remarkable is its icy surface, which is covered in frozen nitrogen. This reflective coating bounces back about 70% of the sunlight that strikes it, making Triton shine brightly in the darkness of space. Despite being so far from the sun, where temperatures plummet to incredibly low levels, Triton is geologically active. It holds the title of the coldest geologically active object in the solar system. The surface temperature hovers around -391 degrees Fahrenheit. Yet beneath its icy crust, there may be a subsurface ocean. The evidence for such an ocean comes from Triton's surface, which features a patchwork of ridges, plains, and other unusual patterns. These mosaics hint at cryovolcanism, volcanic activity involving ice rather than molten material. Voyager 2, during its flyby in 1989, captured images of geyser-like plumes on Triton, which are believed to be caused by nitrogen gas escaping from beneath the surface. Sunlight might heat the nitrogen trapped under the icy crust, causing it to build pressure until it bursts out in spectacular plumes. This process creates smooth patches on Triton's surface, further supporting the idea of active geological processes. Triton's capture by Neptune likely had a significant impact on the planet's moon system. In the past, Neptune may have had more moons, but Triton's arrival could have disrupted their orbits, either ejecting them into space or causing collisions. Today, Neptune has a smaller number of moons compared to planets like Jupiter or Saturn, and Triton dominates the system in both size and mass. Neptune plays a significant role in shaping the distant Kuiper Belt, a region beyond its orbit filled with icy objects, dwarf planets like Pluto, and countless comets. Despite its vast distance from this belt, Neptune's gravitational pull influences the movements and orbits of many objects within it. This long-range gravitational interaction, known as resonance, helps explain why some Kuiper Belt objects, such as Pluto, follow very specific orbital patterns. For instance, Pluto is locked in a 2-to-3 resonance with Neptune, meaning that for every 2 orbits Pluto completes around the Sun, Neptune completes 3. The idea that Neptune has influenced the Kuiper Belt so profoundly ties into a fascinating hypothesis about its past. Many scientists believe Neptune wasn't always located where it is now. According to the migration theory, Neptune might have originally formed closer to the Sun and then gradually moved outward to its current position. This migration process likely stirred up the young solar system, scattering smaller objects outward. As Neptune settled into its new orbit, it may have helped trap certain objects in the Kuiper Belt within its gravitational reach. Without Neptune's influence, many of these objects might have been ejected entirely out of the solar system or sent hurtling inward toward the Sun. In addition to creating resonances, Neptune's gravitational presence likely prevented a full-fledged planet from forming in the Kuiper Belt. Instead of coming together to form a large planet, the icy bodies in this region remain small and scattered. By controlling the dynamics of this region, Neptune has played a crucial role in maintaining the current structure of the solar system. Well, Neptune remains one of the least explored planets in the solar system, and it still holds many secrets waiting to be uncovered. One of the biggest mysteries about Neptune is its internal composition. Scientists know it's primarily made of water, ammonia, and methane, but the exact structure of its interior remains unclear. Does it have a global ocean beneath its thick atmosphere, or is its core more like a solid rock? These questions are hard to answer without sending spacecraft closer to study the planet. Another intriguing mystery lies in understanding how Neptune and other icy giants like Uranus formed. While gas giants like Jupiter and Saturn have been studied extensively, the unique properties of ice giants suggest they followed a different path of formation. Scientists are eager to learn how these planets gathered their icy compositions and why they emit so much internal heat, especially since Neptune emits nearly 3 times the energy it receives from the Sun. While Voyager 2 provided groundbreaking data in the 1980s, modern telescopes like the James Webb Space Telescope are now revealing Neptune in greater detail. However, telescopes alone are not enough. Spacecraft specifically designed to orbit Neptune or conduct close flybys could provide the detailed measurements and observations necessary to unravel its mysteries. The next generation of missions could revolutionize our understanding of Neptune and its role in the broader story of our solar system. Exploring this distant planet isn't just about learning more about Neptune. It's about uncovering the processes that shaped our solar system and perhaps even gaining insights into similar planets around other stars. With the rapid advancement of space technology, the day we unlock Neptune's secrets might not be too far away. The idea that life might exist in the far reaches of our solar system is both intriguing and motivating, driving numerous scientific missions. This curiosity is rooted in our desire to understand our place in the universe and the conditions under which life can thrive. While Mars has been the centerpiece of planetary exploration, Titan presents an entirely different set of conditions that could foster life. Unlike the barren, rocky landscape of Mars, Titan has a thick atmosphere, liquid lakes, and a complex chemistry that scientists believe could be key to understanding the potential for life in extreme environments. Titan is not only Saturn's largest moon, but also the second largest moon in our solar system. Its size, coupled with its unique atmosphere and surface characteristics, makes it an object of immense scientific interest. Titan is enveloped in a thick atmosphere primarily composed of nitrogen, with significant amounts of methane and trace gases. This atmosphere is unique among moons in our solar system, creating a greenhouse effect that raises its surface temperature slightly above what would be expected given its distance from the Sun. Titan's surface is also covered with a variety of organic compounds, and it's home to lakes and seas of liquid methane and ethane. Despite Titan's extremely cold temperatures, which average around negative 290 degrees Fahrenheit, and its lack of sunlight, scientists believe that life could potentially exist there. The thick atmosphere, presence of liquid, and complex organic chemistry suggests that under the right conditions, some form of life might thrive on this distant moon. Titan's environment is both alien and intriguing. Its dense atmosphere, vast landscapes, and surface liquids offer a rich tapestry for scientific study, particularly in the search for life. Titan's atmosphere is predominantly nitrogen, similar to Earth's, but with a substantial presence of methane. This methane plays a crucial role in Titan's weather systems, forming clouds, rain, and even lakes and seas on its surface. The atmosphere also contains a variety of organic molecules, which are essential building blocks for life. The surface of Titan is a complex and dynamic environment, characterized by vast plains, towering mountains, and deep impact craters. Beneath its icy crust lies a subsurface ocean of liquid water and ammonia, a potential haven for life. The surface itself is coated with a thick layer of organic material, likely formed from complex chemical reactions in the atmosphere, which then settle onto the surface. Titan's geological activity is unlike anything on Earth. Instead of molten rock, cryovolcanism on Titan involves the eruption of water, ammonia, or other volatile substances. These cold volcanoes release methane and other gases into the atmosphere, contributing to the complex weather patterns observed on the moon. Cryovolcanism is a process where low-temperature substances like water and ammonia erupt from a planetary body. On Titan, this process may help sustain its thick atmosphere by replenishing methane, which otherwise would be broken down by sunlight over time. These cryovolcanoes also indicate that Titan is geologically active, with potential energy sources that could support life beneath its surface. Titan's surface is dotted with lakes and seas of liquid methane and ethane, the largest of which is Kraken Mare. These bodies of liquid are replenished by rainfall from the methane-rich atmosphere and possibly more cryovolcanic activity. These lakes and seas present a stark contrast to Earth's water bodies, but could serve as habitats for life forms adapted to these alien conditions. The possibility of life on Titan, while speculative, is rooted in the Moon's unique conditions. Life on Titan would be unlike anything found on Earth, requiring adaptations to extreme cold, limited sunlight, and a methane-rich environment. Any life on Titan would need to withstand temperatures far below the freezing point of water. This means that life forms, if they exist, would likely have protective mechanisms to insulate against the cold, possibly using antifreeze-like substances in their biological processes. Titan receives only about 1% of the sunlight that Earth does, making photosynthesis as we know it unlikely. Life on Titan would need to rely on alternative energy sources, such as chemical reactions. This could involve the breakdown of methane or other hydrocarbons, processes similar to those seen in certain extremophiles on Earth. The chemistry of Titan's lakes and atmosphere is vastly different from Earth's. Life forms on Titan would need to utilize methane and ethane as solvents in their biological processes, a stark contrast to the water-based life on Earth. This would require a completely different biochemistry, perhaps using cell membranes and enzymes adapted to work in these hydrocarbon solvents. The search for life on Titan focuses on its unique environmental features, each offering a potential habitat or clues to the presence of life. The lakes and seas of liquid methane and ethane are among the most promising places to search for life. These bodies of liquid could harbor microorganisms that have adapted to the extreme cold and chemical composition of these lakes. Researchers are particularly interested in areas where liquid and solid phases of these hydrocarbons interact, as these could provide energy gradients that life could exploit. Titan's atmosphere contains hydrocarbon clouds, formed from methane and ethane. These clouds, along with the organic molecules they contain, might play a role in chemical processes that could support life. Studying these clouds helps researchers understand the atmospheric dynamics of Titan and the potential of prebiotic chemistry. Titan's diverse surface features, including its dunes, river valleys, and mountains, are formed by both sedimentary and geological processes. Some features, like river valleys, suggest the presence of flowing liquids, which could be crucial in the search for life. Ongoing geological activity, such as cryovolcanism, could provide heat and energy sources necessary for sustaining life in subsurface environments. Titan has been the target of several exploratory missions, each contributing to our understanding of this enigmatic moon. The Cassini-Huygens mission, launched in 1997, was the first to conduct a comprehensive study of Saturn and its moons, including Titan. The Huygens probe successfully landed on Titan in 2005, providing the first direct observations of Titan's surface and atmosphere. The data collected from this mission revealed a landscape strikingly similar to Earth's, with rivers, lakes, and seas, but composed of hydrocarbons instead of water. Despite the wealth of data, no direct evidence of life was found. Scientists continue to analyze data from the Cassini-Huygens mission while planning new missions to further explore Titan's potential for life. The focus is now on understanding the moon's subsurface ocean and its interaction with the surface, as well as the complex chemistry of its atmosphere. Set to launch in 2026, the Dragonfly mission is one of the most ambitious efforts to explore Titan. This mission will send a drone-like rotocraft to Titan's surface, capable of flying between multiple sites to conduct scientific experiments. Dragonfly will focus on Titan's dune fields, impact craters, and possible subsurface reservoirs of liquid water. The mission aims to search for prebiotic chemistry and potential signs of life by analyzing surface materials and atmospheric samples. Dragonfly's mobility will allow it to cover a broad range of environments, providing a comprehensive look at Titan's habitability. One of the most compelling aspects of Titan is its rich organic chemistry. Titan's thick atmosphere is laden with complex organic molecules, including methane and ethane. These compounds, considered the building blocks of life, form in the upper atmosphere and precipitate down to the surface, creating a unique chemical environment. The presence of these molecules suggests that Titan has the potential for prebiotic chemistry, similar to early Earth conditions before life began. Energy is crucial for life, and Titan presents several potential sources despite its distance from the Sun. Sunlight, though minimal, reaches Titan, but it's insufficient to sustain life as we know it. Instead, chemical reactions may serve as the primary energy source. Reactions between methane and other hydrocarbons, or between organic molecules and surface minerals, could provide the necessary energy for life. Additionally, cryovolcanic activity might release heat and chemicals that could support microbial ecosystems in subsurface environments. While Titan's surface is dominated by liquid methane and ethane, the possibility of a subsurface ocean of liquid water mixed with ammonia is particularly intriguing. Liquid water is a key ingredient for life as we understand it, and ammonia could act as an antifreeze, keeping water liquid at Titan's frigid temperatures. This subsurface ocean could offer a stable environment where life might exist, protected from the harsh surface conditions. Titan is one of the coldest places in our solar system, with surface temperatures averaging around negative 290 degrees Fahrenheit. This extreme cold poses a significant challenge to life, as biochemical processes typically slow down or halt at such low temperatures. Any potential life forms would need specialized adaptations, such as antifreeze proteins or other mechanisms to maintain cellular function. Titan is exposed to significant levels of radiation from cosmic rays and solar wind. While its thick atmosphere provides some protection, radiation still poses a threat to potential life forms by damaging DNA and other critical molecules. On Earth, some extremophiles can survive high radiation levels, suggesting that if life exists on Titan, it may have similar protective adaptations. Oxygen is essential for most life on Earth, but Titan's atmosphere contains almost none. Instead, it is primarily composed of nitrogen and methane. Life on Titan would need to thrive without oxygen, relying on alternative metabolic processes, such as anaerobic respiration, which does not require oxygen but uses other molecules as electron acceptors. Spectroscopy is a key tool in studying Titan's atmosphere and surface. By analyzing the light absorbed and emitted by Titan, scientists can determine the composition of its atmosphere and identify various organic compounds. This technique has revealed the presence of complex hydrocarbons and nitriles, providing insights into Titan's potential for life-supporting chemistry. Missions like Cassini-Huygens have been instrumental in exploring Titan. The Huygens probe, which landed on Titan in 2005, provided direct measurements of the Moon's surface and atmosphere. Data from landers and probes help scientists understand Titan's geology, weather patterns, and chemical processes, offering clues about its habitability. While landers and probes provide valuable data, sample return missions would allow for more detailed analysis using sophisticated laboratory equipment on Earth. Collecting samples from Titan's surface or atmosphere and bringing them back to Earth would enable scientists to conduct high-precision experiments, potentially uncovering signs of prebiotic chemistry or even microbial life. Titan's unique environment, rich in organic molecules and with potential subsurface liquid water, make it a prime candidate in the search for extraterrestrial life. While no direct evidence of life has been found yet, the complex chemistry and intriguing geological features suggest that Titan could harbor microbial life forms, particularly in protected subsurface habitats. The future of Titan exploration looks promising with missions like the Dragonfly rotorcraft, set to launch in 2026. Dragonfly will explore Titan's diverse environments, from its organic-rich dunes to potential cryovolcanic sites, searching for signs of life and prebiotic chemistry. Continued advancements in remote sensing, lander technology, and sample return missions will deepen our understanding of this enigmatic moon. Well, for now, we can hope that the next few decades of research hold the potential for groundbreaking discoveries that could reshape our understanding of life in the universe. Don't forget to subscribe to the channel, and if you want to know more about outer space life, then watch our video on how the first 100 years of colonizing Mars would look like. See you in the next one. Bye.